Physical science time. We're talking today. Oh,
Sorry.
oh,
It was like really entertaining.
Gunner! It's Gunner! We'll have to, someone after this class, not right now, and this is just a joke, so please don't do it. Someone will have to FaceTime Gunner and ask him for his opinion about what he's learned from Chapter 5 so far. LOL. Okay. That's so cute. Okay, we're today talking about work, power, and machines. This is, when I was in elementary school, we were told about simple machines. You've heard about simple machines before too. You know what simple machines are. I took that when I was in elementary school as like one of the fundamental things that we think about in science. It really isn't. Kind of in the same way that like I took the order of the planets to be one of the fundamental things we talk about in science. No one ever talks about the order of the planets after you've known the order of the planets. Once you have the simple machines memorized, you don't really talk about the simple machines anymore. But what you do is we kind of use this discussion about machines to discuss how work can change. So it's not really about, let me tell you it this way. What I'm not concerned about is that you have memorized what all the simple machines are. There are questions on the test about what are the simple machines and what do they do. But mostly what we're worried about with simple machines is how do they change the quantities involved in work. What is work? Great question. Some of you have very poor understanding of what work is. I'm just kidding.
You're not wrong.
Yeah, there's some of these cowboys won't even lift a finger to do something. But that's not the kind of work we're talking about. Right, remove from your head right now the idea that work is something that is hard and you get paid for, because that's not the kind of work we're talking about. Maybe that's an actionable definition of work for your daily life, like your mommy says, you need to dust today, or I'm going to delete your Instagram account. I don't know your life. I'm trying to make up things that are relatable to you. That kind of work is not what we're talking about. We're talking about the physical definition of work. Work in physics. Work in physics. Work in physics is W equals F cross D. That is really not legible at all on the... You can kind of read this in real life, maybe? I don't know. Let me rewrite this one at least. But on camera, it's really not. Is that better? Yeah. It's certainly not worse. Mm-hmm. Yeah, it is. This is the thing we need to talk about, though. What's this little guy? Yeah, we use it at the elementary level to mean times. That's not all it means. In physics, especially in higher level physics, we have a different definition of this. And we're not going to go super far into it. It has to do with trigonometry. Have you heard of things like sine, cosine, and tangent? Have you heard of those? Nope. Okay, but we're not going to talk about that right now. When you get to physics, I would hope that there's at least somewhere between 5 and 10 people in this room who will take physics eventually in 2 or 3 years when you have that option. When we get into that, we do the trigonometry that's involved in this, but we won't do it today. What this means for us right now, this little thing here, is called cross product. And for now, we will use it just as multiplication, but what it means for us, imagine, well, let's talk about the other things first. Work, W is work, F is guess. Guess. Hunter already guessed, and he was right. No?
Friction.
No.
Force. Distance.
Force.
Oh.
Force. Lowercase d is distance. What do we measure the quantity distance in physical science? Or in any science? No. Distance. Meters. In the SI, what do we measure forces in? Newtons. Work, then, is newtons. If work equals force times distance, then the unit for work is newtons times meters. Newton meters, we often say. Really astute observers of physical science will remember that this Newton is a kilogram times a meter divided by a second squared. If we multiply that quantity, a Newton, by a meter, what does that give us? Do you remember? Well, first of all, let's just do the math. If it's a kilogram times a meter divided by a second squared, we multiply that by meters, what is it now? Let's just simplify this expression. So bring down the first expression, or bring down the first term, kilograms times meters squared over seconds squared. And what did this equal? We had another separate symbol for this. What was it? Ramrock.
Joules.
Yeah! Joules. Joules.
Ah!
So we measure work in joules. Now, wait. Another Ramrock. Why would, what else did we measure? This is not for the Ramrock. The next question will be for the Ramrock. What else do we use to measure joules from chapter 4? Well, we can use any kind of, energy. We used energy as the quantity we used to measure joules. So what is that telling us about work? This is for the Ramrock. What is the fact that work is measured in joules and energy, kinetic energy, potential energy, was measured in joules? What does that tell us about work? Work is a type of energy. Type of energy. Yeah, Taylor does, and I think Carson and Fate said it at the same time, so they both do. But we're going to do that afterward. You'll have to remind me. Type of energy. Work is a type of energy. How do we define energy in chapter 4? This is a very important concept, so let's redefine it. What is energy defined as?
The ability to make something change.
Perfect, Hunter. You get a Ramrock too. The ability to cause change. Okay, so now we have these several pieces of a puzzle. Let's put them all together. Let's do it in this way. The key thing here about work is that a force has to be applied when we're talking about physical work. A force must be applied in this is extremely important. This is where people get thrown off all the time. This is where trick questions with trick answers like no solution in math appear. A force must be applied in the same direction as distance traveled. I wish I had another marker. When we're talking about work, I'm going to just read this again, and you're all going to write this down. This is so important, and we're going to talk about some examples. When we're talking about work, a force, F, must be applied in the same direction as distance. A force must be applied in the same direction as distance traveled. What does this word direction remind you of?
Vector quantity.
Vector quantity. In fact, if we're being really good about what we were doing at the beginning of the year, work is a vector quantity and force is a vector quantity, and this distance is a vector quantity. So let's do the example now. Who's tough guy? Dalton. Here's Dalton. Those are Dalton's arms. And I put a hat on you, Dalton. Those are Dalton's arms. There's two of them, though. Okay, good. Those are Dalton's arms. Now, imagine Dalton, what's something that you hoist commonly at your job, Dalton? What do you lift? Calves. Okay, great. Thanks for making me draw a calf.
Oh.
It's a dog. It's just a sheepdog. Okay, so Dalton will lift this sheepdog. Which direction, if he's lifting a sheepdog, which direction is the force acting? Up. So we can say F is up. Okay, which direction does the calf move? Up. Which direction is D going then?
Well, if you could even lift it.
He can, of course he can. He's a tough guy, Chloe. Okay, so the force is applied up and the calf goes up. Was work done? Well, let's go. Don't answer yet. Let's go back to our definition. When we're talking about physical work, a force must be applied in the same direction as distance traveled. Was work done? Work? Yes. Okay? That's example 1. Seems pretty simple. Here's example 2. Who's another tough guy? Keslin. I'm going to draw her orange, obviously. She's a redhead. Here's Keslin. Keslin, what's something that you hoist commonly? Barrett, yes. Shoes. Okay, I'm going to draw shoes because I think that's funny and it's easier. There's some shoes. Keslin is lifting shoes. She's not wearing shoes, and neither is Dalton, but she is lifting shoes. Okay, so let's imagine Keslin in her orange coat and her orange hair, and she's lifting shoes. She's holding shoes up. Which direction is she applying force on the shoes? Up. F is up. But now, she's walking across the floor. Which direction is she moving? She's moving, in this case, right. Is work done? No, they're not in the same direction. So you're going to get a question on your test that says something like, there was a question on your last test about Myrtle and her shopping cart. Myrtle is holding up a shopping cart. I don't know why she's holding it up. Its wheels broke or something. She has to lift it. But she's applying a force upward. She's holding up a shopping cart, and she's walking through the store. Is she doing work? No, they're not in the same direction. Now, where we get back to this cross product is that to whatever extent they are the same direction, and this is just for your information, this is not on the test, and just I want you to recognize that where the complicated math can come in. Imagine who mow lawn? Will's wearing a green shirt, so Will's going to be wearing green. Will's mowing a lawn. Will's got curly hair, so that's what that looks like.
Not right now.
Be quiet, Will. Okay, Will's mowing a lawn. Shh. Will's mowing a lawn, and he's applying a force down and to the right. That's how the handle works. He's applying a force down and to the right, but the lawnmower is just going right. Well, guess what? It's somewhere between these. It's somewhere between yes and no, meaning that part of the force is being done as work, but not all of it. And what we would do is we would take W equals the force times the cosine of the angle theta times the distance. This is a mathematical function that you will learn how to do, I think, in Algebra 2, but I don't really remember. But we take this angle between these two things, this angle theta here, is how we would calculate that in the future. Don't worry about that. That's not part of the math for this chapter. What I'm getting at is to however much the force and the distance do match, that amount of work is done. So in this case, where they match perfectly, all of the force goes into the work equation. In this one, where they don't match at all, none of the force goes into the work equation. And in this one, where they kind of match, some of the force goes into the work equation. And we can figure that out using slightly more advanced math than freshmen use. Let's do some math real quick here, and then we'll move on to another thing, which is power. Let's say Dalton, in his example, Dalton is applying a force of 100 newtons. Oops, not green. Dalton's not wearing green. Where'd my eraser go? Okay, in my example with Dalton, the force equals 100 newtons up. The distance, let's say he lifts the calf or sheepdog, whatever it was, 0.5 meters. Okay, there's our given. I'm going to erase this definition of work here real quick, or this explanation of work.
What's the word in the middle of the F and D on the lawnmower?
Cosine theta.
What?
You don't need to worry about it. It's COS, and then the Greek letter theta, which represents an angle measure. You should probably know that. Aren't you in geometry? The theta is a Greek letter that's used to represent some angle. Shh. Okay, be quiet. Now, what's the first thing I need to do for my equation? Don't forget.
You need to write that. Raw equation.
What is the raw equation here?
Force W equals F times D.
Yep, W equals F cross D. Now we
X equals cross product.
yes, it does. Very good. Substitute. Tell me what's right.
We'll put working as lawn.
What?
There's nothing for W yet.
Thank you. 100 newtons cross
100 yards.
0.5 meters. Okay, and then last step. Shh. It's right here, Taylor.
Oh,
Last step. Last step. Last step.
It'll just be like
50 what?
joules.
Joules. 50 joules. So what the questions will sometimes be phrased like this. In this example, was work done? Answer? Yes. How much work was done? 50 joules. 50 joules of work was done. Could you, we're not going to do an example of this right now, but could you, if it said something like, Dalton used 50 joules of work to lift a 100 Newton sheep, how far did he move the sheep? Could you do that? Yeah, you just have to do what other step? What other step would have to manipulate? Okay. I'm going to erase this, what's up here, and we're going to start talking about power, and you guys can continue writing down that example if you like. Shh, okay, you're being a little too loud. Power. Shh. Power equals what? Does anyone remember?
2.
Power equals, oh sorry, no. Okay, I'm just going to write work divided by time. Or power equals energy divided by time. Either is fine. Why would these two things both be fine? They're different variables. What did we already talk about?
Same thing. Weight is energy.
This is weight.
I mean,
Work is a type of energy. So if we're given an amount of work, we can use this one. If we're given an amount of energy, we can use this one. Power equals work divided by time, or power equals energy over time, which is P is power. Capital W is work. T is time. And capital E is energy. In what SI unit do we measure energy? Joules. In what SI unit do we measure time?
Seconds.
Seconds. In what SI unit do we measure work we just talked about?
The one thing, you know what I'm saying?
We just talked about it. Joules.
Yeah, that's it.
So, if power is energy divided by time, or work divided by time, and work or energy are measured in joules, and time is measured in seconds, power is measured in joules per second. No, just joules per second. And this quantity is abbreviated as a watt, capital W. You've heard of this because there's the amount of power a light bulb emits is measured in watts. The amount of power a microwave oven emits is measured in watts. The amount of power a subwoofer in the back of a delinquent's car emits is measured in watts. Someone's like, I got to get that 350 watt subwoofer, and what they're talking about is how much power the subwoofer is capable of exuding, how much energy in each amount of time. Gabriel, who I wish was here today, Gabriel and I just finished, kind of finished building a computer, and we had to get a new power supply because the first one was a 65 watt power supply, and Gabe thought it would be better if we had a 75 watt power supply. And what that's telling us is how much energy is being used by that power supply every second. Have you heard the unit watt before? Okay. So power is measured in watts. The only thing, this is just a standard equation that you can solve just like you solve equations, but the only thing to be careful of is if you have to solve for time, make sure you get it, remember since the time starts out in the denominator, make sure if you're solving for time, if you manipulate to solve for time, that you get it in the numerator first. That's very important. Okay? So power is how much energy something uses per unit of time. The lab that we sometimes do for this chapter, is we walk up the stairs and then we run up the stairs. And which one uses more work? Nope, you're wrong because you don't understand. That was a little bit mean. You're wrong because you're using the term work to mean something that's hard that you have to do. That's not what I mean. I mean the physical definition of work. Which one uses a greater force? Which one do you weigh more during?
Walking.
What? What kind of answer is that? Listen to me.
The first one was a trick.
No. Listen to me. The amount of force that you put is your weight. You're hauling your weight up the stairs. Which one, walking or running, do you have a greater weight during? Neither. Of course not. Your weight doesn't change between when you rock and roll. Not appreciably anyway. You're having the same weight. Which one do you go a greater distance? We're running up one flight of stairs. Which one do you go a greater distance?
Same.
Neither. Thank you, Aaron. God bless you. No. So we're doing the same amount of work both times. The same amount of force over the same amount of distance. But which one uses more power?
They're the same.
No, they're not. Because what else does power depend on?
How much force you use? Time.
Time. So which one takes more time and therefore less power? Walking. Which one takes less time and therefore more power? Running. So you use more power when you run, but it's the same amount of physical work. Last thing we're going to talk about here. I'm going to erase this. Last thing we're going to talk about here is the idea of simple machines. You need to have memorized the types of simple machines. 1, that's review from elementary school. 2, it's in your vocab words. 3, it's also in your book. Did everyone hear what I just said? You have to have memorized the 6 types of simple machines. Okay? You can do that on your own. Yeah? There are 6 types. Memorize them. Memorize what each one does. Now what we're going to talk about, though, is why use a simple machine at all. What it allows us to do is, look at this example. Let's think of one of the most simple machines, which is the inclined plane. In this drawing, we're going to have an inclined plane. And in this drawing, we're not. Here's a moving truck, and here's a moving truck. It's the same moving truck with the same height, h, from the ground. Okay? So it has some height, h, from the ground. And in this one, tough guy is just lifting up boxes from the ground into the truck. And in this one, some other tough guy is sliding boxes up the ramp into the truck. Well, you can even tell just from the arrows that I did, if work equals force times distance, what is the difference between these? In this one, what is greater? He's moving at a greater distance. A greater distance. He's moving at a greater distance, and so what must be less then? Well, work, in this case, work equals a big distance, and therefore a little force. He only has to use a little force. And in this one, he's moving at a little distance, and so he must use a larger force. So why would we use simple machines? They can change, they cannot, what they can't do is they can't increase or decrease the amount of work done. Let's write that down. Simple machines do not change amount of work. What do they do? Well, they change the ratio. They change the ratio of force and distance, or the direction. What's a pulley do? If you have a, I can. Here's my object. I can lift this maybe, I don't know, maybe 10 Newton object. I can lift it straight up. Look at that. But if I have a pulley attached to it, it's still going to take 10 newtons of force, but now I can pull it down. Like, imagine there's a pulley on the ceiling. I can now pull the rope down, and the chair comes up. So that changed the direction. And why would that be an advantage? Well, for one thing, the human body is better at pulling things down. You can pull with a greater force down. Like you could, if you had to, you could just like hang on the rope and use your entire weight to pull the rope down. Whereas if you're lifting it up, you just have to lift it up. So all that a simple machine does is change the ratio of force and distance or the direction of the force and distance. Simple machines do not change the amount of work.
That's it?
That's the law of conservation of energy. Remember that from chapter 4? They do change the ratio of force and distance or the direction.
They do change ratio.
Other questions?